In this section, we're going to discuss colligative properties, particularly freezing point depression and boiling point elevation. Anytime you add a non-volatile solute, a solute which does not evaporate readily, to a liquid, this extends the boiling point range which the liquid remains a liquid. So we will have something of a freezing point depression and a boiling point elevation. In the freezing point depression and boiling point elevation are what we call colligative properties, because they do not depend on the type of solute but on the number of solute particles in solution. And so when you have salt trucks salting icy roads, what happens is we have a freezing point depression in which the freezing point of ice is lowered, and so it melts at a lower temperature, and so cars don't slip as they're driving. In order to understand how we calculate freezing point depression and boiling point elevation, we need to understand a term called molality. Molality is different than molarity. Molarity is the uppercase M is defined as the moles of solute over liters of solution. However, molarity or molality is lowercase m, and it's defined the moles of solute over kilograms of solvent. Notice I said kilograms of solvent, not liters of solution. The solution contains the solute and the solvent, so that's the difference here. With that being said, let's calculate the molality of a solution containing 17.2 grams of ethylene glycol with this molecular formula dissolved in 0.5 kilograms of water. Okay, so it says we need moles of solute, but we have the grams. So how do we go from grams to moles? Molar mass of ethylene glycol. Alright, so we have 17.2 grams of C2H6O2, and for every 46.08 grams I have 1 mole of C2H6O2 ethylene glycol, and this is over kilograms of solvent, and I already have kilograms, so don't need to do any further conversions on the solvent. And so you should end up with a molality of 0.747 molal solution. Okay, let's use molality to calculate the freezing point of a 1.7 molal ethylene glycol solution. Ethylene glycol is your antifreeze. Again, we put ethylene glycol in your car as antifreeze because it depresses the freezing point, and so it does not allow your engine fluids to freeze at 0 degrees Celsius, but even below 0 degrees Celsius. So let's see what the freezing point of a 1.7 molal ethylene glycol solution would be. You've seen in the previous slide here that your delta TF, which is your freezing point depression, it's the change in temperature of the freezing point in degrees Celsius, can be figured out by taking your molality times in it by a KF, which is the freezing point depression constant for the solvent. In this case, your solvent is not ethylene glycol, because we see ethylene glycol solution. Ethylene glycol is mixed in water, so your KF is known for water to be 1.86 degrees Celsius per kilogram solvent per mole solute. Okay? So let's see. We have the molality. Molality is 1.7 molal, which is moles of solute over kilogram of solvent. And when you take that and you multiply it by 1.86 degrees Celsius kilogram of solvent divided by moles of solute, you see how your units end up canceling out, and you're left with degrees Celsius, which is your change in temperature or change in freezing point. So in this case, it would be 3.2 degrees Celsius. But we're being asked what is the freezing point right now. Not what we figured out right now is the delta TF, which is the change in temperature of the freezing point. So if we want to figure out what the freezing point is, we have to say, we know that freezing point is 0 degrees Celsius. I'm getting ahead of myself. 0 degrees Celsius. And we know that we decreased this by 3.2 degrees Celsius because this is freezing point depression. And so our new freezing point is negative 3.2 degrees Celsius as opposed to 0 degrees. So our water, or our engine and our liquid, won't start to freeze till it hits negative 3.2 degrees Celsius as opposed to 0 degrees Celsius. Okay, go ahead and give this one a try. Calculate the freezing point of a 2.6 mole sucrose solution. We're going to use delta TF, molarity, times our freezing point depression constant, which is known, and the molarity is known, and this is known, so we would know what is our molarity, 2.6. Again, this is moles of solute over kilograms of solvent multiplied by the KF, which is 1.86 degrees Celsius, kilograms of solvent over moles of solute. You see how our units cancel and we're left with degrees Celsius? So you should get a value of 4.8 degrees Celsius. But this is just the freezing point, or the change in temperature of the freezing point. But we need to actually figure out what the freezing point is. So freezing point is normally 0.00 degrees Celsius. And we depressed it or decreased it by 4.8 degrees Celsius. So our new freezing point is negative 0.48 degrees Celsius. And that is our final answer. Okay, now you may look and say, okay, let's calculate the boiling point elevation of a 1.7 Molo ethylene glycol solution. You may say, okay, I thought ethylene glycol was antifreeze, and it depresses our freezing point so that the liquid in our cars doesn't freeze at 0 degrees Celsius, but at a lower temperature. It's also will increase the boiling point. Why? Because it is a solute in a solution. Anytime you put a solute in a solution, it decreases its freezing point and increases its boiling point. So not only is ethylene glycol used to prevent freezing in engines in cold climate, but it also prevents the boiling of engine coolant in hot climates. Okay, so let's go ahead and do this problem. This time we have a new equation, similar idea, but we'll do delta T of B, in which is the change in temperature of the boiling point here. It's our molality times our Kb constant. The Kb constant is what? It's our boiling point elevation constant for our solvent. Again, it's for the solvent, which is water in this case. And this is a value that you can typically look up. For water, it's 0.512 degrees Celsius per kilogram solvent over moles of solute. Okay, so we have molality and we have Kb. So let's see what this brings us to. 1.7 mole, which is moles of solute over kilogram solvent, times 0.512 degrees Celsius kilogram solvent moles of solute. And you see how these cancel, and I'm left with degrees Celsius. And so I get a value of 0.87 degrees Celsius, but that's just the delta T of B. That is the change in temperature of the boiling point. I'm asking you, what is the new boiling point? What is the boiling point elevation? So boiling point is typically 100 degrees. Let's see. 100 degrees Celsius for water solution. And so if we add ethylene glycol to it, it should increase its boiling point by 0.87 degrees. And our new boiling point of the ethylene glycol solution becomes 100.87. Okay, now we're going to, you go ahead and give this a try. Calculate the boiling point of a 3.5 Molo glucose solution, and replay the video to see if you have the correct answer. Now, if we're trying to do the boiling point, we want to use the delta T of B. The only difference is we take molality times our Kb constant instead of our Kf constant. So here we have 3.5 moles of solute per kilogram of solvent. And then we have 0.512 degrees Celsius kilograms of solvent over moles of solute. You see these cancel, and we're left with degrees Celsius. And so this gives us a value of 1.8 degrees Celsius. But this is the delta T of B. So the actual boiling point is 100 degrees, but we have to increase that by 1.8 degrees Celsius. So our new boiling point becomes 108.8 degrees Celsius. Do more practice problems if you need to, and go ahead and study the next section about osmosis. It's mostly conceptual, but you need to take a look at that as well.